In this class, we study angular momentum. Angular momentum is very similar to the linear momentum that we have studied until now, but it is related to the rotation. Before we begin, let us review what we have done with the linear momentum. We have a coordinate of a particle and mass of the particle. And once we have coordinate, we have velocity. We multiply the time derivative of the coordinate by the mass to obtain the linear momentum. And then we obtain the kinetic energy, that is in this form. Or we say this is a coordinate and this is a conjugate momentum. And kinetic energy. We are looking for the rotation version of these theory. The rotation is about an axis and head and by an angle theta. And this angle does not carry any dimensions. The coordinate of the rotation is called angle theta. So this is not length. We are interested in how to fill in this part. Okay, let's see. First of all, there are kinematic variables of rotation. Unlike the displacement, we have angular displacement, and this has the dimension of length. This does not carry any dimension. This is dimensionless quantity. So first, before we compute the displacement, we need to identify the position. So the angle, position, angular displacement is the shift in the angle. So remember, we are keeping the direction of axis of rotation the same for during the rotation. Next, we consider the ratio of the displacement to the change in time. Ratio of the displacement. Here, there should be n vector. This should be vector, vector. This is delta theta n hat divided by time. And take the limit, delta t goes to 0. Take the limit, delta t goes to 0. So this is a velocity. And this is angular velocity. Angular velocity. And we have a special notation just like a velocity v. We have omega, angular velocity. We can take another time derivative to find it as an acceleration. Special notation. So if I take the derivative, then we have a special notation for the angular acceleration. That is alpha, angular acceleration. If we consider the rotation, it is very important to identify the change of the position vector on the rotation. Every information we require is contained in the famous Rodriguez formula of a three-dimensional finite rotation. Without this, we cannot go ahead. In many textbooks, they do not show the whole picture. They only show a partial picture, and they do not introduce the full story and do not tell you the truth, but just indirect information of interpreting the final result. It is very stupid to not to introduce the correct fact as it is. So this is the reason why I introduce you Rodriguez formula of a three-dimensional finite rotation. This is true for any angle. That's quite important. For any finite value, it is correct. And any infinitesimal limit, it's still correct. The basic idea is that you can decompose a vector along a given axis. That is, right now we are interested in the axis of rotation. If you look at this figure, Rodriguez rotation formula is quite simple. First of all, we decompose a vector x that is being rotated about the axis of rotation and a half. Any vector has a component that is parallel to n. That component is n dot x. And there is another component that is a perpendicular component, x per, that is x subtracted by x parallel. That means x minus the x component can be decomposed into the parallel component and perpendicular component relative to the axis of rotation. And under rotation, the parallel component is invariant. That's quite important. And the perpendicular component varies, and magnitude of the perpendicular component, because it's on a circle, magnitude of the perpendicular component is invariant. However, the component has a new generates a new component, and that direction, the same component, the perp direction, is being decreased. Let's see. This is a p. This is a p. The axis of rotation, and yellow one is a parallel component. Yellow one is a parallel component, and this purple line indicates the perpendicular component, and perpendicular component rotates to arrive at point Q at angle theta, and the magnitude is x perp. X perp is this one. And the magnitude of the original perpendicular component was x perp, and it is being rotated. So the projection onto the original perpendicular component is x perp cosine. X perp cosine. And there is a new direction that is perpendicular to the x perp, and that is also perpendicular to the axis of rotation. That is this direction. So we use E3 and E1 hat and E2 hat and expand this final vector in terms of E1, E2, and E3. So we have identified E3 is n hat, unit vector. E1 is x perp's unit vector. So x perp magnitude divided by the x perp divided by x perp magnitude. So if I multiply E1 hat x perp magnitude cosine theta, what I obtain is this one cancels. E1 hat x perp magnitude cosine theta. Because x1 is a parallel to x perp, this is just x perp cosine theta. So this is x perp cosine. This is x perp cosine. And this one is x parallel. X parallel is invariant. X perp becomes x perp cosine theta, and the perpendicular component has the magnitude x perp magnitude and E2 perp, E2 hat and sine theta. What should I do? I have two vectors, x vector and n vector, and E2 hat is proportional to n cross a and n cross x. And n cross x has the magnitude x sine, let me say phi. That phi is independent of theta. This is phi, the angle between n hat and x. And that component on the plane, we have E3 hat equals n hat, and x, we have angle phi. So x, this is phi. This magnitude is x sine phi. That is x perp magnitude. Aha. X perp magnitude is x sine phi, and including this unit vector, E2 hat x sine theta is actually n cross x. That's the reason why we have a sine theta here, and remaining all pieces are combined in here, n cross x. So this is a very nice identity, very useful identity from which we can describe the rotational motion of a particle very easily. This is called Rodriguez formula of a three-dimensional finite rotation in three dimensions. In summary, x is being rotated about the axis and hat with the angle theta. In that case, parallel component. This is the parallel component, and this is the perpendicular component x perp, and this is x parallel. X parallel is invariant, and x perp shrinks its size, and the perpendicular component rises up with the sine theta, and including the magnitude of the radius, we can simply write it in terms of n cross x. So this is the formula. Now we replace x prime of theta with x theta, and x in terms of x of theta equals to 0. Then we can take the derivative of this x as a function of theta. Before we go ahead, we recall the x perp. X perp is, we have a special name, lever arm vector or moment arm vector. In addition, n cross x is the same as n cross x perp, because x is composed of x perp and x parallel, and x parallel is always parallel to the axis of rotation, and cross x is x parallel plus x perp, and x parallel is parallel to n hat. Therefore, this one does not contribute. So x perp, this is enough. So this is a useful identity. Basis vector in a uniform circular motion, we have derived everything. The plane, axis of rotation and hat, it is rotating on a surface that is normal to this plane. This is E3 hat. The original x vector has x per direction perpendicular to axis of rotation. We use E1 hat, and we use E2 hat that is parallel to the n cross x. That's it. So these three coordinates, E1, E2, E3 coordinates are well defined. Velocity and acceleration of a rotating particle. We just copy the formula, replacing this, carrying out this replacement, and take the derivative with respect to theta, and then using chain rule, take the time derivative of that angle. So that is a theta dot and time angle derivative. Angle derivative, it used to be, what was that? Cosine. Cosine, and this was sine. So cosine becomes a minus sine, and sine becomes a cosine. And then chain rule gives another vector, theta dot. So that is the velocity. When we put angle theta equals 0 for at any moment, then this one vanishes because sine 0 is 0, and this one becomes a 1, so cosine theta equals 0 is a 1. So we arrive at a very important formula. The velocity of an object that is rotating about the axis and hat with the angular velocity theta dot, it is making uniform circular motion if theta dot is constant, or even though its theta dot is not constant at that instant, it becomes theta dot and hat cross x, or x perp, either way. And theta dot and hat is called the omega, angular velocity. Omega cross x is the time derivative of that object. That's quite interesting. In addition, if this x is fixed, f is fixed and keeps on rotating, in that case, the acceleration can be computed in a similar way. I mean, time derivative is replaced with omega cross. So double time derivative is to be replaced with the omega cross omega. And we begin with position, and position is fixed. In that case, I can make use of the back cap rule. Back cap rule, A cross B cross C, back B, A, back, A to C, cab, back cap rule. Because we have omega cross x, and this is A, this is B, and this is C, right? So B is omega, and AC, omega dot x minus AB, omega squared cx. We can factor omega, magnitude omega squared out. So minus omega squared, then this is x factor, and this is minus n hat. We are familiar with this expression. What's that? This is x parallel, and this is x minus x parallel. That means x perp. So lever arm vector. So acceleration of an object that is making a uniform circular motion due to the rotation about the axis n experiences acceleration along the direction is opposite. This is minus x perp direction minus lever arm toward the center of the circle, and the magnitude is omega. So minus omega squared, magnitude is omega squared minus omega squared x perp. So this is quite interesting. In general, it is possible to have a variable angular velocity. So set the double dot does not have to be 0. In that case, we have velocity is still omega cross x. If I take the one more time derivative, what I get is velocities, angular velocities derivative, nx plus omega cross x, because x dot equals omega cross x. Here, let's see, x dot equals omega cross x. X double dot equals omega dot cross x plus omega cross x dot. And this one is we used alpha to be omega dot angular acceleration cross x, and then using this relation, here we have omega cross x. This is what we already obtained, and we have an additional piece. This is centripetal acceleration toward the center of the axis of rotation, and this is angular acceleration, spinning more rapidly, or deceleration, or either deceleration or acceleration along the tangential direction. Orbital angular momentum and kinetic energy. Now, velocity on object who has a displacement position fixed in space, but with the axis of rotation, if it rotates about this axis with the angular velocity omega, then it acquires a velocity that is tangent to the radius, the planar radius. Planar radius is the lever arm vector. That is omega cross x, and this is omega cross x, or omega cross x perp, that is a lever arm. This parallel component doesn't contribute at all. All right. So with this expression, we can compute the kinetic energy. 1/2 mv squared. And v dot, this is a v squared, omega cross x squared. This is sine square theta, rho minus cosine square theta. So square subtracted by scalar product square. And again, this is, if I pull this theta dot square out, then this one becomes x vector squared minus theta dot square is pulled out, x square minus n hat dot x. Okay, this is square. Actually, we don't need this one. This is n dot x square. That's it. So that is x square minus x parallel square. That means x perp square. X perp square. So kinetic energy is written in the form 1/2 mx perp square level arm square times the theta dot square. Now we recall the kinetic energy of a linear momentum linear system. Particle moves with the velocity, and p is mass times the velocity, and the kinetic energy is p squared over 2m, or 1/2 mv squared. In a similar manner, we arrive at the same quantity energy, kinetic energy. Relative to x, we have theta. Relative to x dot, we have theta dot. Relative to m, we have m x perp square. That's quite different. And energy. If we write down the energy, we used to have momentum squared over 2 times the mass squared. And here, kinetic energy is explicitly given. Let us define I to be I x perp square. And this one is momentum inertia, rotational inertia. If we define in such a manner, kinetic energy is like that, and why don't we introduce mass times velocity was the linear momentum. We define angular momentum, that is this rotational mass, rotational inertia, times angular velocity. That means m x perp squared theta dot squared. Using this expression, rotational kinetic energy can be expressed as in I theta dot squared 1/2 I theta dot squared over I. So L squared over 2I. The rotational inertia is a mass times distance squared, that is lever arm squared, x perp. Okay, lever arm squared multiplied by mass. Then we can write down the kinetic energy to be 1/2 I theta dot squared, or 2I L squared, where L is the angular momentum, I theta dot. In comparison with the linear momentum case, 1/2 mx dot squared, or p squared over 2m, where p is the mass times velocity. We have an orbital angular momentum is I theta dot, and I is a mass times x perp squared. Let us consider orbital angular momentum. In classical mechanics, we have angular momentum, so orbital angular momentum only. But in quantum mechanics, there is another angular momentum that does not involve the orbital motion. So it is called the spin angular momentum. But in classical mechanics, any angular momentum involves the rotation, explicit rotation about an axis. We recall that there is a coordinate x and its a time derivative called the velocity, and mass times time derivative of coordinate is called momentum. And this coordinate and momentum is always in pair. So that's the reason why they are conjugate. So linear momentum P is conjugate to the coordinate x. And once you know the linear momentum, because it is well-defined, time derivative of coordinate multiplied by its mass, kinetic energy is 1/2 mass times time derivative of coordinate, that is velocity squared. Or if I make use of the conjugate momentum concept, it's p squared over 2m. This one appears also for the rotation, and here rotation has the coordinate angle theta that does not carry any physical dimensions. We have kinetic energy, that is 1/2 I theta dot squared, and I is mass times momentum squared. We follow the same rule to define angular momentum L, that is I times theta dot. So I carries another dimension length squared in comparison with the mass in the linear momentum. This one compensates the dimensionlessness of the coordinate for the rotation. Anyway, back-cap rule was very useful to identify this export square. Let's see. Let us rewrite this orbital angular momentum. Orbital angular momentum as a product of momentum inertia and angular velocity. And it was written in the form as a product of mass and lever arm squared. And this is a scalar. And this one is a vector. We recall that x per, let us compute the x per times cross products x dot. And x dot for a rotation, x dot is velocity, and velocity is omega square, omega cross x. And because it is the same, if we replace x with the lever arm vector, let me substitute lever arm vector in here and apply the back-cap rule. Back, B, A, B, C. Back, square, cap, dot product. And we find this x dot we know theta and theta dot, we for a fixed axis rotation, this one and x per lever arm vector, they are making a right angle, so this one does not contribute at all. So the only contribution is a theta dot multiplied by x per squared. If we substitute this result in here, so theta dot multiplied by lever arm squared is replaced with x per cross, there's m is carried in here, x per cross x dot. And if m is multiplied to the x dot as a product. So this is a linear momentum. So linear momentum cross product with the Lebesgue vector. Linear momentum, that is a tangential direction. And we have a Lebesgue vector x product. And that is the same as we replace this one with the x, because x parallel does not contribute to the rotation. And that is always perpendicular to this plane, x parallel. Therefore, I can substitute x per plus x parallel, and still this one does not contribute. So we can safely replace this orbital angular momentum in terms of a cross product of x and linear momentum. This is another definition of the orbital angular momentum. We continue to consider the rotational version of Newton's second law. Now, the orbital angular momentum is expressed as the cross product of x and linear momentum. And we replace this p with mass times velocity. We define the core torque to be x times cross product with F is the external force on an object. We find the time derivative of angular momentum is cross p plus x cross p dot. And we find this is mx dot. The parallel vectors cross product always vanishes. The first term is a 0. This one is 0 vector, and this one is a plus x cross f. This is torque as we have defined, and therefore Newton's second law of motion for the rotational motion is angular momentum's time derivative is torque. The linear version, time derivative of linear momentum is force, and torque is x cross force. That's it. Let us extend this result to a system of particles. We have n system of particles, and each particle has its own angular momentum, and every angular momentum is expressed as xi cross pi, and pi is mxi dot. So I replace it. We expressed in terms of the information for the center of mass. Any position vector of a particle can be expressed in terms of the center of mass and the relative coordinate. So ith particle xi is the position from the center, from the origin, and we have a cm, it's xcm. Then this is the relative, the position relative to the center of mass. So we substitute this one in this formula, and mi is pulled out. The position is expressed in terms of the sum, and we have velocity, it's time derivative. Unlike the case of the linear momentum case, we computed the total mechanical energy. In that case, the expansion involves xcm dot plus xi vector bar dot square. But in this case, there are four. The expansion gives four different terms. The first term is the mass times x cross velocity of the CM. The second term, mi CM cross product with the relative coordinate velocity. And the third term, we have this term, cross velocity of the CM. The last term is relative position relative to the center of mass, relative velocity relative to the center of mass. In here, we consider this contribution. This one, if I substitute this result, so xi subtracted, this one is xi subtracted by xcm. Okay? Then this summation will give mass times the central mass. The next one is identical to that. So this one vanishes. If it is 0, its a time derivative is also 0. Sure, we are working in the framework of non-relativistic theory in which mi dot vanishes. So these two disappears. I can sum this mass to find this one is capital M. So capital M multiplied to the velocity of the center of mass is the linear moment, total linear momentum of the system of particles. So center of mass position cross product with its total linear momentum. An object, there's a CM, it may acquire some torque so it can rotate, but in addition, without structure, with respect to the center of mass, it can make a rotation with respect to the center of mass. This is the orbital angular momentum of every particle relative to the center of mass. So total linear momentum is the sum of the total linear momentum of the center of mass as a point particle and the angular momentum relative to the center of mass. Now, let us try to compute this one. We recall self-interaction is not allowed due to the Newton's third law. And we would like to sum all of the contribution to contribute to the torque. What is the torque? Net torque should be sum of all of the torque applied to ith particle, and all of the torque applied to ith particle is due to the external force on that object and internal force due to the remaining pieces. In comparison with the previous calculation for the linear momentum conservation, we have the different piece, x cross. The summation is doubled and multiplied by 1/2. The two particles, xi and xj, communicate each other with the same magnitude but opposite direction force. So I can replace this one with the negative sign. Then the sum of these two contributions becomes xi minus xj cross fj to I. In case the force is central, if it is central, then central force is proportional to the displacement between the two objects. The cross product disappears, absolutely. So we have a stronger requirement for the angular momentum conservation. But anyway, if the internal force is central, then the net torque on a system of particles is net external torque on a system of particles. And the internal torque due to the force that is central always vanishes. The angular momentum conservation derives from this formula. Total angular momentum's time derivative is the net torque, and net torque must be external. Internal torque does not contribute at all as long as the force, the internal force, is central. If the net external force is turned off, then the time derivative of total angular momentum of the system of particles vanishes. That means total linear momentum, angular momentum of a system of particles vanishes as long as the internal force is central. Next, we consider rotational portion of the work kinetic energy theorem of Coriolis. We remember the kinetic energy for the linear version. Linear version, 1/2 m x2 dot square minus x1 dot square. And that was the same as differential of 1/2 m x dot squared during the motion. Okay? That was time derivative of the kinetic energy. Integrate over time, something like that. We have a carbon copy. We replace x with the theta, m with the I. I is mx per square. That's it. And work kinetic energy theorem states that this one is the same as force times displacement. Delta kinetic energy is the force times displacement. In here, this force is m x double dot dx. And it is replaced with the time derivative and the time integral. So one half dt. These were the same. In a similar manner, what we have to do is replace mem with the rotational inertia, x double dot with angle theta with vector. This one should be correct even if we replace this one as a scalar product. And I double theta dot is actually the, L equals I theta dot. So L dot, as long as I is invariant, it becomes I theta double dot. So this one shows f dx is replaced with tau dot d theta. So f dx integral is the work, tau dot d theta is the work in the rotation portion. Rotational inertia of a continuous mass distribution is sum of x per squared mass. If mass distribution is continuous, then dm is to be replaced with rho times the volume. And we have done such a calculation a lot of times when we carry out the proof of the shell theorem. We began with the computation of a one-dimensional case along a circle on a disk and a sphere. In these cases, we have rewritten the spatial integral into the polar coordinates r dr. R meaning the volume, the radial direction differential dr, arc along the polar angle is r d theta, arc along the azimuthal angle is r sine theta d theta. So volume d cube x is r squared dr d phi sine theta d theta, and this one was rewritten into the d cosine theta. So if we consider a sphere of radius capital R, we used radial integral becomes something like that, and we have d cosine theta. Cosine theta runs from -1 to 1, and d phi that runs from 2g to 5. This is just a volume integral. And then we have additional piece, x perp squared. X perp squared. X perp, that is relative to the axis of rotation. Let me call this one as a z-axis. This is x, and this is x perp, origin. So x magnitude is r, and this is, we have theta, that means this is r sine theta. So x perp squared, this is r squared sine squared theta. So this integral should be done, and we know how to do that. The radial part, angular part, every part. We have done a lot of work, so I do not reproduce the kind of straightforward calculation in here. But proof of Huygens-Steiner parallel axis theorem. Here, there's a useful relation. During such kind of calculation, it will be very useful to apply this. That is, I have an axis, and I have computed rotational inertia about this axis, but we have another axis that is a parallel, n hat and n hat prime. And this parallel axis has the perpendicular distance h. So this is a vector h. So if I want to compute this rotational inertia, what I have to do is x perp squared dm. And x perp is measured relative to n hat. And if I want to compute the rotational inertia about n hat prime, then I have to compute the x perp prime squared dm, and x perp prime is x perp plus h. This is displacement. Because of this, if I substitute this one in here, I have three pieces, but this one is exactly the same as the central mass. But the problem is we have the original value, and that is central mass is in here. Central mass is along the original axis. Therefore, original axis rotate. This integral gives x perp. Average value is the central mass, and the central mass is the origin. So this one becomes 0. It does not have any perpendicular distance from the n hat. That's the reason why we know this XCM, that is the rotational inertia about n hat, is the same as the n prime that is parallel to this axis, except that there is additional piece should be added to have the value for n hat prime. Application of this calculation for the specific geometric objects are given listed in here, and the way how to evaluate, how to write down the mass differential mass and change the variable, the useful trick are listed all here. This is a uniform thin rod. We have 1/12 ml squared thin rod, thin rod 5. This one, for example. And the uniform disk of radius r, 1/2 mr squared. If I rotate this in this way, uniform sphere radius are sphere, and I have a rotational axis. At the end of the day, you will find 2/5 of mr squared spherical shell that is empty inside, that has a bigger two-thirds of mr squared. Okay, in summary, we can review the Rodriguez formula for finite rotation in 3 dimensions. Rotation of vector x about a fixed axis and head by a finite angle theta gives the transforms of this x0 to x of theta in this way. And this one can be used to find the derivative of x to find the velocity and acceleration. So please review the lecture to reproduce the result for the velocity and acceleration. In addition, until now, we have restricted ourselves for the case when n hat is fixed. However, it is not always true. N hat does not have to be parallel. Does not have to be parallel. It can rotate. And in most general case, at least the rotational kinetic energy is concerned, we have this formula. And this formula states that if we expand everything altogether, we can expand in terms of Cartesian components of theta I dot, and theta 1 dot, theta 2 dot, and theta 3 dot. Kinetic energy is not expressed as just a theta 1 dot squared and nothing else, but it is a completely most general case carries all kinds of 30 contributions, theta 1 squared, theta dot 2 squared, and theta 3 dot squared, and theta 1 dot, theta 2 dot, theta 1 dot, theta 3 dot, and so on. There are so many contributions in fact, in reality, for the rotational kinetic energy. If we expand everything all together, the way to find out the coefficient of theta I dot and theta j dot, we can take the partial derivative twice for the rotational kinetic energy. Then you will find very strange matrix. It is called the inertia tensor. While we learned the case for the scalar, however, the inertia, the moment of inertia is not a simple number, but in general it is a 3 by 3 matrix. A rather complicated one. However, this matrix, explicit form of this matrix is quite symmetric. We can exchange a row and column, any row and column. We will find that it is transpose of this matrix is the same as its own matrix. The strange, this very simple structure of this symmetric matrix made us possible to find the principal values. Actually, the principal values are for the fixed axis rotational inertia, and in fact, there are three independent principal axes. But that is out of the scope of this first year class, but you will find it's a very interesting problem to solve. And if you find out the very basic nature of this inertial tensor, then perhaps you will be far advanced students than who just compute numbers using the matrix algebra. Okay, that's it for today.